Try loading a 1 terabyte dataset into memory on a single machine using standard tools like Pandas, and you will immediately hit a wall. Your memory maxes out, the process crashes, and your analysis stops. Apache Spark solves this by distributing the workload. If you divide that same terabyte of data into smaller, manageable chunks across a cluster of 50 connected computers, the processing finishes in minutes. To harness this power in Python, we use PySpark. PySpark is essentially an API wrapper. You write your instructions in Python, but under the hood, Spark translates that code and executes it on the Java Virtual Machine, or JVM, which handles the high-speed distributed processing. The engine operates on a master-slave architecture. Your application runs on a central driver node, which analyzes your code and builds a task plan. It then hands it off to a cluster manager. The cluster manager allocates the necessary hardware resources and spins up multiple executor nodes. These executors hold the partitioned data in memory and carry out the physical computations in parallel. Getting started requires setting up the entry point to this cluster. You initialize a Spark session and use it to read your source files, like a CSV, into a DataFrame. From there, you can apply basic transformations, selecting specific columns or filtering rows, exactly as you would in standard Python analysis libraries. Moving the workload from a localized hard drive into the distributed memory of a cluster removes hardware bottlenecks. You scale your scaling processing capacity to match the size of your data, simply by adding more nodes to the network. When you string together a dozen complex filters and groupings in PySpark, the code seems to execute instantly. This is an illusion created by lazy evaluation. Spark doesn't touch the actual data when you define a transformation. It simply records your intent, stacking up those instructions inside a logical plan. The execution engine waits until you call an action, like .show, .count, or .write. The moment that action hits the queue, Spark takes your logical plan, optimizes it, and breaks the workload down into a cascading tree of jobs, stages, and individual tasks for the executors to process. This execution process runs smoothly until you introduce custom Python user-defined functions, or UDFs. Applying a standard Python function to evaluate a column of data forces Spark to step outside of its optimized JVM environment, causing a massive drop in processing speed. Because standard Python cannot run natively on the JVM, Spark has to serialize the data into a binary format, send it across a bridge called Py4j, execute your Python function, and reserialize the results back to the JVM. This serialization happens row by row. If you process a billion rows, you cross that boundary a billion times. Syntactically flawless Python code can easily crash a cluster if you ignore the mechanics of the JVM. Writing efficient pipelines requires staying within the boundaries of the underlying execution engine. When joining a massive table with a tiny one, you might notice the entire cluster hanging. To match records, Spark must group corresponding keys on the same physical machine. This forces a network shuffle, moving massive amounts of data across the network. If your data is heavily skewed towards specific keys, one single executor node gets overloaded with traffic while the others sit idle. You eliminate this bottleneck by executing a broadcast join. Instead of shuffling the massive dataset across the network to find matches, you duplicate the tiny table and send it directly into the local memory of every single executor. The nodes process their partitions locally, bypassing the network transfer entirely. Let's test this logic. Look at this standard Python UDF designed to multiply 2 columns. Pause the video now and try rewriting this logic using either native PySpark SQL functions or a Vectorized Pandas UDF. When deploying this code to cloud infrastructure like AWS EMR, the physical realities of the cloud dictate your pipeline design. Cloud storage systems like S3 do not behave exactly like the native Hadoop file system. Read and write operations are slower, making partitioning strategies critical. Most importantly, the driver node runs on a single physical machine. If your driver runs out of memory from collecting massive results, your entire job terminates. Producing a functional script locally is only the first step. Engineering a resilient pipeline means actively managing memory footprints and minimizing data movement across the cloud network. We refine a heavy, inefficient script into a production pipeline by controlling the flow of data at every stage. We start with predicate pushdown. By moving our .filter conditions to the very beginning of the query, we drop irrelevant records before they enter the processing stream, drastically reducing the volume of data the executors have to handle. Next, we strip out the custom Python UDFs. We replace them entirely with native functions from PySpark SQL functions and handle missing values using native.na.fill commands. This keeps the execution locked securely inside the optimized Java virtual machine, eliminating the Py4j serialization penalty. For our data joins, we wrap the smaller lookup tables in a broadcast command. This forces the executors to keep the table in memory, preventing expensive network shuffles when merging the sets. Finally, we address storage and execution configurations. We save our intermediate and final outputs as Parquet files using snappy compression, avoiding bloated CSVs. We also verify that adaptive query execution, or AQE, is enabled, so Spark can monitor shuffle statistics and adjust our query plan in real time during execution. This optimization sequence reduces to 6 core rules. Use data frames instead of RDDs. Filter data as early as possible. Prefer native functions over custom UDFs. Broadcast your small joins. Output and Parquet with snappy compression. And enable adaptive query execution. Screenshot this list for your next deployment. Writing effective PySpark code requires understanding the physical machine limits beneath the syntax. By anticipating how data moves across the network and controlling how it enters memory, you ensure your pipeline scales efficiently across any cluster.